Hi, welcome to the Bioinformatics Chat. My guest today is Markus Schmidt. Markus is a PhD student at Hanyang University in Seoul, South Korea. And Markus and I will be talking about seeding for read mapping. Markus, welcome to the podcast.
Hi, thanks for having me.
So, Markus, read mapping is essentially read alignment, right? And we could use the traditional alignment algorithms. So I think algorithms like Needleman-Wunsch or Smith-Waterman, the algorithms that probably every bioinformatics student learns like as one of their first algorithm. Why are those algorithms not sufficient for read mapping? Why do we need something else?
Okay, well, so there's actually two reasons. The first one is pretty simple. They're way too slow. So the Needleman-Wunsch and Swiss-Waterman algorithms are dynamic programming algorithms, meaning they open a matrix that's on the x-axis would be the genome for read mapping, and on the y-axis would be the read. And then they have to compute a score for every cell in this matrix. So their runtime is the size of the reference times the size of the read. And if your reference is the whole genome, then this runtime becomes so huge because it's a squared complexity that they will just take way too long in order to be practical. So then the other reason is we have in reads, we have structure variants. Usually we don't map the reads against the genome they actually come from, because if we already know the genome the reads come from, then there's no point in sequencing that genome again. So we map the reads against a proxy genome, something that's similar but not completely the same. And then we have structure variants. So maybe one read is actually, let's say there's a huge translocation between two chromosomes, and then the read is partly from one, partly from the other chromosome. And the Needleman-Wunsch and Swiss-Waterman algorithms don't currently or cannot deal with this kind of situation. Maybe you could use the Swiss-Waterman and get the two best Swiss-Waterman alignments in this case, but then there are other cases such as inversions where both Swiss-Waterman and Needleman-Wunsch don't really work.
Right, and so the alternative, one of the first alternatives to simply the dynamic programming algorithm was the BLAST algorithm, and it uses this notion of a seed, and the whole paradigm is perhaps known as seed and extend. So how does that work, and what is this idea of seeding?
So I think it's seed and extend, or seed chain and extend. I think sometimes it depends how detailed people want to be when they say that. And the idea is you want to use short sequences that are extremely similar between the read and the reference to first get an idea where to actually look for your alignment. And by getting these seeds, you can then kind of maybe cluster them, find an area where there's a lot of seeds, and then just do dynamic programming in this area to get the best alignment. And that way you don't have to dynamic program over the entire reference.
And so the idea is that these seeds are very easy to find, right? So the simplest form of a seed is just a k-mer, and then you can do like a hash map lookup. You can immediately know. So you can take a k-mer from a read. And you can look up exactly all the locations where the k-mer occurs in the genome. Is this roughly how it works? And what are the steps involved?
Yeah. So the idea is you can, before even starting your read alignments, you can take the reference by itself and compute an index for the reference. And that might be a very expensive step, but you only have to do it once because your reference never changes because you're always aligning against the same genome. And then when your read comes along, you can then use that index to very quickly find these seeds. And there's a few different classes of seeds. For example, fixed size and variable size seeds. So fixed size seeds would be perfect matches, so no errors. It's the sequences in the read and the reference must be completely equal. But you have a predetermined size, and that's what you already mentioned, the k-meres. And then variable-sized seeds, the seeds can have different sizes. We have perfect matches, so no differences, but the seeds can have different sizes. And then there's also some other forms as gapped seeds and various others. Probably you can come up with a lot of different ideas here.
And so for the fixed-size seeds, we have k-mers. And we also have other forms. So, for example, we have minimizers. Can you explain briefly how minimizers work and why can they be better than k-mers?
Yeah. So I would go over an intermediate step. So k-mers is literally the simplest form of seed, as you already said that you can have. You just take all k-sized matches between a read and a reference. And then the idea is, well, if we take all k-sized matches, there's a lot of k-sized matches that are consecutive. So let's say there's a region that's maybe 20 nucleotides long between a read and a reference that matches perfectly, and our k is 5. Then we have a bunch of these k-sized pieces that just follow one another and that overlap a lot. So the idea is, why do we need to compute these extra seeds if we don't use them? They don't give us extra information because we already know this area is overlapping. So why don't we maybe just take every fifth 5-mer, let's say, then we wouldn't have the overlaps. Okay, so that's fine. You can take every fifth 5-mer, and you can do that for computing your index on the reference initially. That means your index will be 5 times smaller because you're taking 5 times less seeds. But then you only have every fifth k-mer of the reference in your index. So then when you want to go with your query and you want to look up the k-mers, you actually have to look up every single k-mer, not every fifth, but every single one. Because if you would also take every fifth and there would be an offset of a single nucleotide, then suddenly your k-mers wouldn't match anymore. And we know that sequences like to introduce 3 kinds of errors. So they substitute nucleotides, they insert new ones, and they delete some. So it's very common actually to get this offsets via the insertions and deletions that are introduced by the sequences. Okay, so that's the initial idea if we want to reduce the size of our index. And that's called a fixed sampling. A fixed sampling, by the way, to take every nth k-mer. But then we still have to look up, for a query of the size 10, we still have to look up 10 minus k many k-mers, plus minus 1. So the idea is, can we also get rid of these duplicate lookups, especially if we know that most of the lookups will not yield results since we didn't actually put all the k-mers into our index. And so that's where minimizers come along. And the idea of minimizers is you take a window of a certain width, and then you look at all the k-mers in that window, you score the k-mers, and you only use the lowest scoring one, that's why they're called minimizers, to either put in the index if you're working on a reference, or to look up in the index if you're on the read.
So you said we are scoring k-mers. What does it mean?
Yes. So the idea is we just want... There's actually like plenty of scoring systems you can define. The idea is that your scoring system just depends on the actual sequence of the k-mer. So it's completely independent of its position. You actually only use the nucleotides of the k-mer to determine the score. And one very simple way to understand how the scoring system works is just to replace all the nucleotides, so the A, C, T, G, by numbers. So A would become 0, C 1, T, and so on. And then you take the k-mer and you just read these numbers out as a consecutive number, and you get, maybe for 3-mer, you get 124. And that's your score. And then you just use the one with the lowest score.
Which is the same as if you compare the k-mers themselves as strings in the lexicographic order.
Yes, you can also use a string comparison, but I mean, it's exactly the same. One thing that's done differently in practice, though, is you don't want your scoring system to be quite as simple as I just described, in order to avoid like very small repetitive sequence. So you don't want maybe A, C, A, C, A, C, A, C to have a low score and then be used as a minimizers all the time. So people come up with a little bit more complicated scoring system that makes sure that these small tandem repeats don't get used as minimizers.
What would be an example of a more complicated, more realistic scoring scheme?
Oh, okay. So there's you can come up with a bunch of stuff. It's really just your creativity is limitless.
So maybe like use a hash function.
For example, you can just use the score and afterwards run it through a hash function. You can also not, for the initial scoring system, we just use the k-mer in the same order that it actually occurs. You can also shuffle them around in a certain way that you always shuffle in around the same way.
And so once we scored every k-mer, we pick a window.
Maybe 10 consecutive k-mers, and then we score all 10 of them, and then we only use the one with the lowest score. So instead of doing 10 lookups, we only do one lookup, but we are very sure that this k-mer will be actually in our index, because we've done the same thing on the reference beforehand. And since the scoring system is completely independent of position, just considers the sequence, we can be sure that, or relatively sure that, we will find this k-mer in our index.
Right, as long as the whatever mismatch we have between the read and the reference, as long as that doesn't affect the minimizer itself, or which one is the minimizer, right?
Yes. So it's surprisingly, if you actually go through and make some examples and play around with it, it actually is surprisingly difficult to put mismatches into a sequence in such a way that you mess up a lot of minimizers. Usually if you put in a mismatch, you will mess up maybe one or two, but then immediately afterwards, even in a window where this mismatch is still part of your window, you will get the same minimizers as without the mismatch. So it's surprisingly stable.
So that was a brief overview of fixed size seeds. And then we have variable size seeds. How do they work?
Yeah. So also, as with the fixed size seed, there are several classes of variable size seeds. Maybe let's start with the simplest one. I would say that's MEMS. So that's maximal exact matches. And MEMS are all matches between a reference and a read that are maximally extended. So a seed is maximally extended if the seed extends to either the start of the query or the end of the query. I'm using query and read as synonyms, or to the start of the reference or to the end of the reference. So it reaches one end of either sequence, or it reaches a mismatch. And that has to happen on either side. So basically, as maximally extended says, you cannot extend the seed anymore in either direction. And if you take all of these maximally extended matches, you get the set of MEMs. And then there's several subsets of MEMs. So there's SMEMs, that's a very commonly used subset of MEMs. And then there's max spanning seeds, which is not so commonly used.
And SMEMs stand for like super maximal
extended matches. And the idea of these subsets is that you use the query positions, and exclusively the query positions of the seeds, to define a subset. So a SMEM is a mem that is not enclosed by another mem on the query. So every mem has an interval on the query, and if you have a mem and in your set of all seeds there's no other mem that completely encompasses the mem you're looking at, then this mem is also an SMEM. And this will filter out some smaller mems, and it filter out a lot of regions that are like, let's say you have a mem that is enclosed, then you know, okay, we have a match here with the reference at one position, but on this match there's it's shorter than another match, that's the enclosing mem, that points to another position. So most probably this shorter mem is not an actual similarity, but just a random match. So this set of SMEMs filters out a lot of wrong or seeds, the misleading seeds that point into the wrong direction.
One way I think to explain it is both MEMs and SMEMs are the seeds you cannot extend, but the definition of extend is different. So for MEMs, by extend, you mean you have a certain location on the read and certain location on the reference, and you extend them simultaneously, right, in place so that they remain synchronized, they remain matching. Whereas for SMEMs, you only consider the interval on the query. And for that interval, you consider all the matches in the genome. And so extend here means you extend on the query as long as there's at least one match in the genome, right? And so when you cannot extend it on the query so that there is at least one match in the genome, then you say it cannot be extended, it's super maximal.
Yes. And all the MEMs you found before while you were still extending, those are MEMs, not SMEMs.
Right.
But you have to make sure that while you're still extending, the MEMs are only those positions that basically you lose during the extension. So a position, you say you're halfway done with the extension, and there's still room to extend left and right on the query, and you have a position on your reference where there's also room to extend left and right. So this would not be a MEM, the connection between these two. Only a position where you can still extend on the query further, but on the reference you're locked in, there would be a mismatch on the left side and on the right side. Then this would be a MEM, and then while you extend further, you eventually lose this MEM, and in the very last step you're left with SMEMs, yes.
So maybe a good way to think about this is that MEMs correspond to pairs of interval, right? One interval on the query, one on the reference, but SMEMs are simply intervals on the query, which implicitly correspond maybe to some intervals on the reference. But when you're extending an SMEM, or when you cannot extend an SMEM, you cannot extend it purely as an interval on the query.
Okay, yeah. Or at least if you would, then you would lose all connection to the reference.
Yep.
Yes.
Yep. And you mentioned the third type, which is what?
Maximal spanning seeds. So that's from me from a previous paper and only used in the aligner I made, so not common at all. And the idea is just to go one step further than SMEMs. Basically, SMEMs have this enclosure definition, and with maximal spanning seeds, the definition is basically for each maximal spanning seed, there must be one position on the query where this seed is the longest seed, period. So you can take the entire position on the entire query interval of your maximal spanning seed. You have to pick one, or there must be one position that you can pick. And when you look at this position, there's no other seed that's longer than the one you're currently looking at that's also overlapping this position. Interestingly, the maximally spanning seeds are easier to compute with the suffix array indices than SMEMs, even though their definition is stricter. It's kind of contradictory, but I think we'll get into that later when we compare the runtimes and quality of seed sets.
Yeah, but just to make a remark, so we have these nested definitions of MEMs. So we have MEMs, and SMEMs is a subset of MEMs, and this maximum spanning
seeds is a subset of the
SMEMs. Which is maybe we can briefly talk about the trade-offs here. So when you move to a smaller set of seeds, you perhaps gain some efficiency, but the drawback is that you lose some sensitivity. So you might lose some matches, some mappings that you would find otherwise.
Yeah, so the idea is basically, since we're just using the seeds to find the correct alignment, I'm basically trying in the paper to talk about the absolute amount of correct information that a set of seed delivers. And with correct information, I mean the amount of information that this seed set, amount of information in that seed set that points towards the correct position on the reference. So by virtue of being subsets, these amount of correct information has to decrease with the smaller subsets. So just because there are less seeds, period, there's no new seeds, the absolute amount of correct information has to decrease with every smaller subset we take. So SMEMs must have equal or less correct information than MEMS, and the maximally spanning seeds must have equal or less correct information than the SMEMs. So then you would say, oh, but then I will always use MEMS because that's the best value for me. That's how I get the most accurate alignments. And yes, you're right, but you also want to consider the efficiency of your seed set. So if you take this amount of correct information, we can define it properly later, and divide it by the number of seeds, then you get a rate. In the paper I call it correctness rate, but basically this rate just tells you how efficient is your seed set. How much time will you need to extract this amount of correct information from all your seeds? Because in order to find where your seeds are pointing, you will have to look at every seed. So your runtime will depend on the number of seeds. And this correctness rate rises with the smaller subsets. So SMEMs have a much higher correctness rate than MEMS. So even though they have less absolute information, in comparison to the amount of seeds you have to sift through to get the correct information, there's way less sifting you have to do to find your information. And then with max spanning seeds, it's even a little bit further. You have even a little bit better correctness rate. But nothing in comparison to the jump from MEMS to SMEMs. From MEMS to SMEMs, there's really a huge jump in this correctness rate.
But maybe you don't necessarily want to optimize for this per seed amount of information or this correctness rate, because then you could end up with a very, very small set which would map very few of your reads, while each seed would be super, super useful for mapping. But then a lot of your reads would remain unmapped.
But you have no seeds left over, but you would be super fast. It's kind of a trade-off. What do you want to achieve? Do you want accuracy, then basically the recommendation is go for a MEMS, but the warning is this will take forever because you have to compute so many more seeds, you have to inspect so many more seeds. Do you want, runtime accuracy trade-off? Then maybe you can look at the smaller seed sets and get faster for the penalty of losing some correct alignments.
Now let's talk about how to compute these variable-sized seeds. So you mentioned the FM index and various variations on the FM index, and I think those would be perhaps best suited to compute SMEMs rather than MEMs. Is that right?
Yes, so there is algorithms to compute MEMs using these indices, but it takes a long time. It's really slow. One reason why that is with the FM index, you have to have a step where you extract all the seeds that you've computed, all the suffix array intervals. You have to extract the reference positions. And this step depends on how many seeds do you have computed. So the larger your seed set, the slower it will be to compute with the FM index. And this last step, this extracting, takes quite some time. And then the same for the extensions. With MEMS, you have to do way more extensions than with SMEMs or maximal spanning seeds. So again, you're losing a lot of time to compute the better seed set.
Would it be safe to say that until now, computing all these variable size seeds mostly relied on the FM index, or were there any other approaches?
So you can compute via fixed size seeds. So by combining fixed size seeds, I don't know if that's what you mean right now, because I think there's also other indices to compute variable size seeds, but I personally have only worked with the FM and one variation of the FM index, the FMD index. So I've not, I don't have much knowledge about the runtime differences. I've seen some aligners that use different so the FM index is a compressed index, and by deciding how much you compress, you can control the memory it takes. And it's like a trade-off. You can make it use more memory, but it will be faster, or you can make it use less memory and make it slower. So I've only always used one implementation, and that's the FM index implementation of BWA MEM, because that's just what we started with, and it's working good so far, and BWMM is a well-used aligner, so we figured it's a good starting point. But there you cannot adjust the amount of compression, so you're stuck to one particular form.
And in your paper, you propose a new way to compute variable-sized seeds from the fixed-size seeds, right? So how did you come up with this idea? Were there already approaches to do that?
So interestingly, there's quite a few approaches that do that. But since I'm from the read alignment area, I've not seen a read aligner that does that, but there's plenty of genome-to-genome aligners that compute MEMS via fixed size seeds. So after we started and I had the draft up of the paper up on bioRxiv, somebody contacted us and was like, hey guys, you should also look into this area with the genome-to-genome aligners. And then after we basically made our algorithm, we found out, oh, there's similar algorithms to this already existent. So yes, there's a few approaches. Interestingly though, we have an optimization in our approach that's not present in the other ones. So we then like kind of turned around the story of the paper a little bit from the, hey, we made this algorithm and to do something new, to the, okay, now we'll analyze more and just present this optimization in the algorithm.
In computing variable size seeds from fixed size seeds, at least on the face of it, seems pretty straightforward. So we talked, for example, about MEMs, which are these pairs of intervals on the query and the reference that you cannot extend any further. And so you could just start with a matching k-mer between the query and the reference and simply extend that k-mer in both directions until you can no longer extend it.
Yes, exactly.
Why is this algorithm not a great one?
Yeah, so as we've discussed earlier, also with the minimizers, there will be multiple k-mers that are kind of consecutive. So if you start extending them all, you basically extend over the same region in the same mem multiple times. And then at the end, you end up with several of the same mem, and then you have to filter out all your duplicates. And so that's all the other algorithms from the genome to genome alignment. They more or less do this in various forms, so that they have various ideas to filter out duplicates and some also to like reduce the amount of duplicates along the way. But our idea is, well, actually you can, during the extension of the seeds, already recognize if the seeds are like the fixed size seeds or what you're just extending into the variable size seeds, if they're overlapping. So if you sort them in a particular manner and then you extend, you know that there's only one possible seed the seed you're currently extending can overlap with. So then you can just check while you're extending, does it overlap now? Okay, extend one more. Does it overlap now? Okay, extend one more. Oh, now it's overlapping. Then you combine them and then you start extending the combined seed. And you just need to sort it in a particular way.
And what is that particular way?
Yeah, it's the obvious question. So you need something called what we call at least the delta values, and it's basically you take the reference position and you subtract the query position, and it's easier to think of that in a a geometrical way. So if you imagine that you have a plane where all the seeds are drawn and your reference is along the x-axis and your query is along the y-axis, then seeds would be 45-degree diagonal lines. And this delta value is basically also this, it's exactly this 45-degree line. So for two cameras to overlap, they need to be on the same 45-degree line. So if you sort them according to these, then you know, okay, now all seeds that might overlap at some point are next to each other in my array. And then you just need to sort them in a way that they appear in order. So for that, you can just sort them after their query positions or their reference positions. It's the same thing now. And then once you've sorted by these two values, so first by the delta values and then all seeds that have the same data value by the query value, then you know, okay, when I'm extending, one seed to the right, then only the seed that's next to it in my array, one after it, can be the one it connects to.
Right. So the delta value is the intercept of those lines, right? Every seed corresponds to this 45-degree straight line, but these lines can differ. They're all parallel to each other, but they differ in their intercepts. But once you say the intercept is the same, it must be the same line. And so two seeds, they lie on the same line, so they essentially give you the same. If they're close enough, right? If there are no mismatches between them, they would give you the same mem.
In between them, they would give the same mem. Yes.
Cool. So that's regarding mem. Can you also reconstruct SMEMs or maximum spanning matches?
So basically, once you have the mems, you can then apply filters to filter out some seeds, and then you end up with the SMEMs or the max spanning seeds. Again, interestingly, this works with sorting the seeds once and then just walking over them. So if you have your set of mems and you computed it from the k-meres or the minimizers, and then this first algorithm that we discussed, then you can sort these seeds again by their query values. So have them in order according to their query positions. And now, since because of the definitions of the SMEMs is just based on the query or the query intervals, and this, whether they enclose each other or not, we can just walk over all seeds in the order they appear in on the query, and we always remember the largest end position of a seed we've seen so far. So if we then arrive at a seed, we can check, is this largest end position that we remember further down the line than the end position of the current seed? And if that is so, then we know this current seed is enclosed, so it's not an SMEM, because if this largest end position is larger than the current seed, then there must be a seed before this current seed that's enclosing it, because we're iterating over the seeds in order of their query positions. Yeah, and so it's just one iteration, and you check this end position and update it for every seed, and then you end up with the SMEMs.
Cool. So we talked so far about k-meres. Does anything change if we reconstruct these mems from minimizers?
No, actually, interestingly, the algorithm, so something changes, but the way we've discussed the algorithm, it already will work also with minimizers. So the idea with the k-meres is, with k-meres, we know that they always overlap, and we know that with k-meres, if we take the pure k-meres, that there's always one k-mere that extends to the very start of a mem, and always one k-mere that is at the very end of a mem. So we actually don't need any extensions at all. We can just merge all the k-meres. Now with the minimizers, there are these gaps in between them, because they're kind of a little bit randomly placed, because they shift around in the windows. So now there might be gaps in between the minimizers, gaps at the front of a mem and gaps at the end of a mem. But the way we've talked earlier about the algorithm to get the mems out of the k-meres, we already talked about this extension. So this extension will work just fine on the minimizers and then extend them into mems. And that's just also, you can see that in another way as well, because minimizers are just a subset of k-meres. So if you take out some k-meres, but you make sure to keep all for at least one k-mere for each mem, then it'll just work.
Can you also calculate the maximum spanning seeds from your mems?
Yes, so there is an algorithm to get the maximum spanning seeds out of the mems, and because maximum spanning seeds are a subset of SMEMs, which are a subset of mems, meaning that this algorithm which works on mems will also work on SMEMs. And it's a little bit more complicated. You have to use an interval tree and a binary search inside, but the main idea of the algorithm is just for this positions. Earlier we said each maximally spanning seeds is defined by a position where it's the longest seed on the query. So we basically jump from these positions, from one of these positions to the next one, and at each position we collect the maximum spanning seed for that position, and basically we use an interval tree to collect the maximal spanning seeds at this position, and then we use a binary search on the sorted seeds to find the next of these positions.
And then I guess you compared the performance, right? So in order to calculate, for example, SMEMs, you have the FM index route, or you have the K-mers or minimizers route. So what did you find when you compared the running times of these algorithms?
So it depends on a few factors. So what we compared for is for PacBio reads and for Illumina reads. But maybe let's just start for the PacBio reads. And what we actually did is we simulated PacBio reads, but with different error rates. So we used we basically applied a factor to the different error rates, and we modulated that factor from 0 to 1 or a little bit over 1. So basically 0 means perfect reads, and then 1 means error reads exactly the same way that we sampled them from a real world data set. And then over 1 means there's actually more errors. And so the different indices behave differently.
Maybe you could provide some intuition, like why would the error rate affect the runtime of your algorithm?
Okay, so that's because it affects the amount of seeds that you will compute. Not so much for the K-mers, not so much for the minimizers, and not so much for the MEMS, but it will affect the runtimes for the SMEMs and the maximally spanning seeds, because those seed sets are defined via the query intervals. So let's say we have a perfect read, and then basically we will have one mem that spans over this entire read. So this mem will be an SMEM, but it will cancel out all other mems from being SMEMs. So suddenly our set of SMEMs becomes way, way smaller, and the same for the maximally spanning seeds. And if we compute this set of SMEMs with the FMD index, we compute it directly, so we don't go over this intermediate step with the MEMS. So suddenly the FMD index has a huge advantage because it just directly computes the one SMEM that we're looking for, or the one maximally spanning seed that we're looking for, whereas the minimizers and the fixed size seeding has to go through this intermediate step where it just computes all the other seeds, then combines them, and then eventually figures out, oh, there was one that spans over the entire query. Why did I do all this extra work in figuring out these smaller pieces that are now worthless?
Mm-hmm. That makes perfect sense, but also makes me wonder whether by knowing the error rate in advance, we have some idea. For example, are we using the hi-fi reads or are we using the noisy reads? We could maybe adjust. If we're using minimizers, we can use different window length, right? Because if it's a very high quality read, we can afford to have a longer window.
Yes, exactly. So in our analysis, we basically found for CCS reads, so for the circular consensus PacBio reads, that's the high quality ones, you actually are faster with the FMD index for computing SMEMs and maximally spanning seeds than via this other route, via the fixed size seeding. But the pure minimizer computation still beats both of them. But then on the other side, if you go to the lower quality reads, the CLR, that's continuous long PacBio reads, so the lower quality PacBio reads, then the SMEM and max spanning seed computation via the fixed size seeding actually outperforms the FMD index. Only when you start to modulate the error rate to almost 0, then it suddenly comes back, but that's basically the same as going over to the CCS PacBio reads. So.
And maybe to connect these terms, these various seeding strategies, can you talk about which real-world read mappers use which seeding strategies, which algorithms?
Yeah, so most long-read mappers actually use fixed-sized seeds, and a lot of them shifted over to minimizers when they came out. And I think what shifted into this direction is Minimap and Minimap 2, and I feel like there was a period after Minimap 2 came out where all the other long-read mappers went like, oh, we now also implemented minimizers, so they went away from the various different seeding techniques that they used before, and now minimizers seem to be almost the standard for long-read mapping. For short-read mapping, there is more variation. But for example, BWMM uses SMEMs, just as an example. So variable size seeds are also actually used in practice.
And what are the trade-offs between variable size seeds versus fixed size seeds? Like if you were, and I understand you are working on your aligner, which we'll talk about in a bit, but how would you pick the strategy? What affects your choice?
Yeah. So one thing that we haven't talked about so far yet in this trade-off is occurrence filtering. So basically, the human genome is very repetitive. I think most everybody knows that. But that actually creates a problem for read mappers. So there are some sequence. Let me backtrack a little bit. So for our read mappers, we have a maximal size of the seeds that we can compute. We cannot say we want seeds of length 100 because the sequencer will introduce errors and the errors occur in a certain frequency. And if we enforce a seed length larger than this error rate, then we will not find any seeds anymore. So our seeds have to be relatively short. So let's say we're limited to roughly seeds of size 16, let's say. The problem is then now there are sequences of length 16 on a human genome that occur millions of times. And if we want to actually create an efficient aligner, then we cannot compute millions of seeds for the same query interval. So we have to filter out these seeds somehow. And that's something that we in the paper refer to as occurrence filtering. And most aligners, I think all aligners pretty much do that internally via different thresholds. And with the FMD index, that's actually pretty easy to do because when initially computing your seed, you compute a suffix array interval. And then each entry in the suffix array interval corresponds to one reference position. So before extracting your seeds, you can actually just check the length of the suffix array interval, and then you know how many reference positions you will get for the query interval you computed the seed for. And then you throw away anything that occurs too many times. And you don't even have to look at it. That's the nice thing about the FMD index. With the minimizer index or k-mere index, we can do that also in a similar way. We can basically, when computing the index for the reference, already take out anything in the index that has too many reference positions. So we have our hash keys, and then we just check, oh, this hash key has 1 million entries on the reference. Okay, let's delete this one. This one doesn't exist. But now we have a difference in the filtering. So with the FMD index, I will first compute my full seed, so the full length of my variable size seed, and then I will decide, do I throw it away because it occurs too many times, or do I keep it? But with the fixed size seeding, this decision on what to throw away and what to keep is done for the fixed size intervals. So my fixed size intervals are smaller, sometimes much smaller than the variable size seed. And it can happen, and actually does happen quite frequently, that all these fixed size subintervals of the variable size seeds by themselves occur too many times, so they get thrown away. But the complete interval, so what the FMD index will compute, that then occurs only a few times, so we would keep it. And so this way, suddenly computing the SMEMs or max spanning seeds via minimizers, or just using minimizers, we are suddenly missing some intervals that we would otherwise have if we had used the FMD index.
Are there any remedies? Are there any clever ideas to avoid that?
No, actually, at the moment, there's nothing that I know of you can get around with this.
So you should just be very careful with filtering, right?
In picking what index you use. And one thing that you can do is minimizers. The hash table lookups are much faster than the FMD index extension. So you can actually set a higher occurrence filter on the minimizers than you would do with the FMD index in order to remedy this difference a little bit. But yeah, that's all you can do. If you want the full quality, then the FMD index, then you should choose the FMD index.
Yeah, that makes sense. But sort of talking about FM index or FMD index versus minimizers, what about using fixed size seeds versus variable size seeds, where variable size seeds are computed from k-mers, right? From fixed size seeds. So if we decided to use minimizers, we would have a choice either to use minimizers themselves as seeds or extend them to SMEMs or to maximum spanning seeds.
Yes.
It seems intuitive that extending to longer seeds is better, like following your algorithm is better. Are there any drawbacks to using MEMS or a subset of MEMS as seeds? So I imagine you're losing a little bit in sensitivity, right? You might lose some valid mappings if you extend your seeds. Any other considerations?
Yeah. Well, interestingly, the long read aligners at the moment do not extend their fixed size seeds into variable size seeds. They actually work directly on the fixed size seeds, and I think the reason for that is you spend some time reducing the size of your seed set with these algorithms to get them down to SMEMs and max spanning seeds. And the only advantage, because as we earlier said, the SMEMs are subsets of the MEMs, and the max spanning are subset of the SMEMs. And MEMs and KMers are actually equal, so you can show that they cover the same intervals on that they show the same equivalences between reference and query. So you can only lose information if you go down this path. What you gain is you also filter out a lot more false seeds. So the question is now, is your seed processing algorithm, so what the aligner will do after the seeds are computed, will start processing the seeds maybe via chaining or some other algorithms, is that thing slower than this path to the SMEMs? Then yes, you should do it. You should go down maybe to the SMEMs and use, or at least to the MEMs and use those in your seed processing. Or is that algorithm actually so efficient that you can directly use the k-mers? Then you just directly use the k-mers. And at the moment, people use the minimizers directly, but I'm not so sure if that's actually because they've tried it out, but more so because it's one less algorithm you have to worry about and one less algorithm you have to implement. So it's just a matter of practicality.
Can you talk a little more about the equivalence between MEMs and k-mers that you mentioned?
So between MEMs and k-mers, it's actually pretty easy to see. You can just take the MEM and cut it down into k-sized pieces, and then you would have the set of k-mers. Because
right, but what is the statement? What does the equivalence actually mean?
Basically, it means if you have the full set of k-mers and a full set of MEMs, they express the exact same thing, just in two different ways. But the MEMs will use less seeds in order to do so than the k-mers.
But they differ in the sense that if you use MEMs as seeds, or if you use k-mers as seeds, you would get a broader set of alignments from k-mers rather than from MEMs, right? Because if you use k-mers from seeds, and then you apply dynamic programming, then you don't assume that the extension of k-mers match exactly. So a dynamic programming algorithm would find more alignments that are not necessarily exact extensions of k-mers. Whereas if you extend them to MEMs, then you essentially guide your dynamic programming algorithm to say, oh, ignore the possibility of inserting a mismatch here or an indel here, but assume that this is an exact match.
Okay. So that kind of depends on how you apply your dynamic programming in the end. So there are some aligners, for example, BWMEM, that just uses the seeds to find a reference interval. And then once the aligner has the reference interval, it will just throw away all seeds and start dynamic programming between the query and this reference interval. So even though he has MEMs, he doesn't use them at all in the final alignment, and he might just go a completely different path because that's the higher score. There are other aligners, and that's especially for long read aligners. They cannot do this anymore because it becomes too expensive with the PacBio or even with Oxford Nanopore reads. And those aligners will only do dynamic programming in between the seats. So they have two seats and there's a gap that they have to fill, and then they will fill this gap. But I think in this case, if you would chain your k-meres and you would have them overlapping, then there wouldn't be the gaps between the overlapping k-meres. So basically where your mem would be, you would have a chain of overlapping k-meres, and then via the chaining algorithm, you just don't do any dynamic programming for that area. And then only once the mem ends, you will do some area of dynamic programming. That's for k-meres. If you go to minimizers, then there might be small gaps in between your seats because the minimizers are a subset of k-meres and there's just some k-meres missing. And you could, with the algorithm where you extend your minimizers to the mems, you can avoid this dynamic programming. Yes.
Yeah. Okay. That's very insightful. Cool. And so do you want to talk a little bit about the aligner that you're working on?
Yeah, so interestingly, I did the aligner first, and basically we did our new seed sets. That's the maximal spanning seeds, and the advantage of that is compared to the SMEMs that with the FMD index you can actually compute them faster, even though they have a higher correctness rate. So you get less seeds with a higher rate of information, and you can compute them faster, and that kind of gives you a speed boost, but doesn't drop off your quality that much. Obviously, you lose some quality because it's a subset of the SMEMs, so by virtue of being a subset, you can never quite get the quality of SMEMs. And then we also did a different seed processing algorithm than the chaining with some line sweep algorithms. Yeah, and then once we were done, we were kind of a little bit wondering about, hey, is the seed set we used actually better? How do we analyze that? Because what we did, just like most other people that do aligners, we analyzed the aligner at the whole thing. So as one black box, throw the reads in, check the accuracy, maybe throw reads with structure variance in, check the accuracy on structure variance. But it would be kind of nice to see the difference between the seed sets, and you cannot just swap out the seed set and leave the backend of the aligner there, because the backend might work better on some seeds than on the other. So that's why we made the second paper where we then started kind of analyzing the different seed sets and also got the idea, hey, we could try to show the equivalence between fixed size and variable size seeding, and then if there's an equivalence, there must be a way to compute variable size seeds out of fixed size seeds. So that's how this all started. Actually, now that I'm done with both of them, I wish I would have done the second one first, because now I know so much more about the seed sets and have so much more information. And then after this, doing the aligner would have been helpful, but that's you cannot know that in advance.
What is your aligner called? Is it released?
MA, the modular aligner. So there's a GitHub for it. The idea is a little bit different than other aligners. Usually other aligners are monolithic structures, so they just build one big C code or C++ code. And then we actually developed it as several modules, so little small pieces of C++ code. And then you can use Python to combine them. So you can basically set up a graph with Python, say this module comes after this one, comes after this one, comes after this one. And then you can tell the C++ code, now go and execute this graph, and it will just run through it. And the idea behind it is you can really start playing around with all the different things. We basically, for the second paper, in order to analyze it, we also used the same structure, and we reused the modules, because it basically allows you to do your analysis in Python and play around with the different C++ algorithms without losing that much performance, because the code doesn't jump back and forth between Python. Once you have set up your graph, it will just run through it and give you the output.
That's a really cool idea.
Yeah, it's more of a toy though, and like I'm experimentally trying things out, then because obviously by doing this more complex structure, it's more complex to use. You have to set it up, you have to install Python, and when you compile it and so on, not just compile your C program and you're done, like with Minimap or VWMM.
But I imagine you ran some benchmarks against the mainstream aligner. So how does yours compare?
Yes. So one thing that we found is that our I think that it's the back end, because now that I've done the seeding analysis, I can say it's definitely not my seed set, because my seed set is a subset and therefore cannot be better quality. But the back end that we use for the chaining instead of the chaining reacts very well if there's large insertions and deletions in your read, and also if your read quality is very bad. If you have long reads with bad quality, then this backend works well.
Well compared to others, right?
Well compared to, for example, Minimap 2. I would say Minimap 2 is state of the art, what everybody uses. So I don't think it's our seed set, because I know now from the second paper that the seed set is a subset of the SMEMs. So basically the quality of the seeds must be equal or less to than what other aligners use. And for example, what Minimap uses. But therefore, it must be, if it's not the front end, it must be the back end. So it must be the chaining that reacts well to large insertions, large deletions, and also very noisy reads compared to Minimap 2, for example. So that's one thing we could show, that basically the accuracy of every aligner will drop off eventually if you decrease the quality of the reads, but our drop off just happens later than Minimap 2's drop off. We are the only aligner that I know of that still uses variable size seeds, so the FMD index at the moment. For their seeding, all the other aligners moved over to some form of fixed size seeding, most to minimizers.
Wait, but you said FM index, so aren't you using your strategy of extending minimizers to...
No, because I did that before, right?
Oh, right. So you haven't updated it to your latest findings?
No, that's not done yet. Basically... mostly what is missing is an analysis again, if it actually helps, what are the differences, but it's on the initial algorithm that I did is for this maximal spanning seed sets from the FMD index. That's what I started with, and that's what's in the aligner, and that's what I analyzed, so that's what I can talk about now comparing to other aligners. It's not quite as fast as Minimap 2, and that's also something I can see now in the second paper again, that minimizers are faster to compute than variable sized seeds. But interestingly, even though a bunch of other aligners like NGMLR, Blazar, and GraphMap, they also use some form of fixed size seeding, we still outperform them with respect to runtime. Yeah, and then at least in my measurements, accuracy for most aligners on high quality read is pretty similar. So there's not much difference there.
Here's an interesting idea, and I think your modular aligner could be well suited to implement it. So what if you were to create, when you index the genome, what if you were to create both indices? So you'd create an FMD index and a minimizer index, and then somehow, when you're giving a large set of reads to align, you would maybe align a few reads and figure out which index works better based on the read quality, based on how many seeds do you get with each approach,
and then maybe even change the seeding seed set that you actually use. So maybe try maximal spanning seeds, and then you realize the quality of reads is so bad, we need to go to a larger set. Actually the modules are there, so I've spent a lot of time on putting the pieces there. So all the modules for the different algorithms, all the modules to the indices are there. Actually, for the indices, I've used the minimizer index from Minimap 2 and the FMD index from BWMM, so I'm a little bit borrowing there. But the actual algorithm for getting the different seed sets, I implemented all of these, and actually you could put that together pretty quickly, probably. The challenge then just becomes to come up with an algorithm that decides when to swap to what and why, and then analyze that and optimize it.
All right, Markus, well, it was great to talk to you. I'm looking forward to seeing your modular aligner as the one aligner to rule them all. That would be exciting.
Well, I feel like most people have decided that Minimap is industry standard and it's working well, so I don't know. I don't consider my chances that high, but I feel like
Oh, come on. So before Minimap appeared, then everyone knew that whatever BWA was the gold standard, or Bowtie was the gold standard. So I
That's
think
true.
there's always room for newcomers.
Well, I at the moment consider it as something like a playground. So I mostly see the audience of MA to people that actually want to play around with aligners, or maybe just parts of alignment. Maybe you just want to do seeding, then it's like a good way. If you want to even start in Python, you can like use the C++ modules as you wish, and then you can access everything in Python and kind of play around with it, get an idea what works, and then maybe afterwards implement the best solution after you've played around and figured out what works and what doesn't.
Right. So we'll have a link to the modular aligner in the show notes. And Markus, thanks for coming on the podcast.
Thanks for having me. It was very fun. I like talking about the research. It's nice sharing and seeing that people are interested.